Hello, my name is Shayan Doroudi, and today I'm going to be talking to you about mastery learning heuristics, understanding the gap between research and practice. And most of what I'm going to be talking about is described in a short paper I presented last year at the AI in Education conference, cited here. If you look at the research in the AI in education and educational data mining communities over the past few decades, you'll find a variety of approaches to knowledge tracing, which underpins efforts to do mastery learning, which I'll describe in a moment. And so here, this is just a sampling of such papers over the past couple of decades that use a variety of state-of-the-art machine learning approaches, such as hidden Markov models, logistic regression, and most recently, deep learning to conduct knowledge tracing. And this field is rapidly growing with more and more papers every year. On the other hand, we have several prominent adaptive learning platforms, such as Khan Academy, Alex, and Assessments that are being used widely by millions of students in K through 12, and in some cases higher ed, every year. So Khan Academy has tens of millions of students, Alex has several millions of students, and Assessments has around 500,000 students using the platform every year. And these numbers might have grown over the past few months during the pandemic, where a lot of people are doing remote instruction using these platforms. So we can say these platforms have wide impact on students, on K through 12 students every year. And they're all using mastery learning in some way, shape, or another. But the reality is that these platforms are actually using heuristics to assess mastery. That is, they're not using any of the AI or data-driven algorithms based on the research I presented on the previous slide to assess mastery. They're not drawing on any of these techniques that are coming from research. They also aren't developing their own algorithms to conduct mastery learning. They're using simple heuristics, which I'll describe in a few slides in a moment. So the question is, why is this gap between all this work happening on the research side and what's actually happening in practice in these platforms that are actually being used to help students learn? Now, one possible hypothesis is that the people developing these platforms aren't aware of the research, or for whatever reason aren't able to translate the research into practice. But that doesn't seem to be the case, or the full story here, because many of these platforms, like Assessments and Alex, actually have researchers who are publishing papers, who are conducting research in communities like artificial intelligence and education. So, they're interfacing with research and they're conducting research, and they might even be using AI algorithms and other aspects of their platforms, but not to do mastery learning. So why is that the case? So the key question I want to investigate in this talk is, are these heuristics that these platforms are using justifiable? In the 21st century, where the age of big data and data-driven algorithms like deep learning, and all of this research actually happening on knowledge tracing and mastery learning, is it still justifiable to be using simple heuristics? Is it defensible? And notice I'm not asking if it's been justified, because these platforms haven't really provided any justification. They just happen to use these heuristics. But I want to see if post hoc, if retroactively we can go and retrospectively, if we can go and analyze these heuristics to see if they actually might make sense. And the main thesis, the main claim I'm going to make in this talk is that commonly used mastery learning heuristics can actually be reinterpreted as model-based algorithms. That is, we can reinterpret these heuristics as actually being sensible algorithms under some assumptions, some models of learning. And then we can go and analyze those models to see, do we think those models are making good assumptions, to see if those mastery learning heuristics are actually reasonable. So before I can dive into the actual heuristics and algorithms that are used, first let's talk about what mastery learning even is. So the basic idea is to keep teaching a student until they display mastery on a given topic, or keep giving the student problems or practice or any kind of activity related to that topic until they've displayed mastery on that topic. And the general idea actually dates back to the early 20th century, with movements such as the Winnetka plan or the Morrison plan, which were proposed by sort of leaders in the K through 12 education space to try to actually improve the quality of education by making sure students actually master the material before they move on. But this is at a broader, more systemic level of implementing mastery learning. But the promise and one of the affordances of adaptive learning platforms is that we can actually possibly assess mastery on a very fine-grained level, which might have not been possible, the early 20th century, or would have been maybe more difficult. But in an adaptive learning platform, or just more broadly in educational technology, we can actually maybe assess mastery on, for example, very specific individual problems and make sure students master those problems before moving on to the next. And so that's the kind of mastery learning we'll be focusing on in this talk. So let's look at a couple of heuristics that can be used to assess mastery in this way. The first heuristic is the n consecutive correct in a row heuristic, or what we'll refer to also as the NCCR heuristic. And this heuristic suggests to keep giving problems on a given topic until the student gives n correct answers in a row. For example, suppose we want the student to get 3 correct answers in a row. When we give the student a problem, they'll either answer correctly or incorrectly. In this case, they answered incorrectly. We can keep giving them problems, then they answer correctly, incorrectly, correctly, etc. We'll see in this case, they've already gotten 2 correct in a row, but then they answered incorrectly the 3rd time. So we keep giving them problems until eventually they get 3 correct in a row. We then assume that they've mastered the topic or the problem, and then we move them on to the next. And the idea is that once they get 3 correct in a row, or 5 correct in a row, that's probably not due to chance that they were able to get it right that many times in a row. So we have some confidence that they might have actually learned the problem that we were trying to teach. So the NCCR heuristic is actually used in practice. One place it's used is in assessments, specifically in skill builders, assignments and assessments. Which is a particular type of assignment that assessments would provide. So teachers can use assessments without doing any mastery learning. But if they're going to use mastery learning, they would be using the skill builders, and the skill builders uses the NCCR heuristic. It's also previously been used in Khan Academy. And currently, or at least recently in Khan Academy was using sort of what I call a soft variant, or we could call it a gamified variant of this heuristic, in that students need to get a certain number of problems correct in a row in order to reach the proficient level. So the Khan Academy provides us several different mastery levels. One of them is proficient. And if they want to reach that level, they have to get several correct in a row. So this is, a heuristic that's used in practice. And we can possibly see one, reason why, which is that it's a very simple heuristic. It's very easy to describe to a student, to a teacher, and it's very easy to implement as well. Another heuristic is what I call the tug of war heuristic. So what this heuristic says is that, so first I'll describe a general version of the heuristic, and then I'll give a more specific version. So the general version says we give I points for each correct answer that the student gives, and we subtract J points for each wrong answer. And then we keep giving problems to the student until they get N points. Right. So the reason I call it tug of war is that it's like you're playing a game of tug of war. Every correct answer pulls you to one side, every incorrect answer pulls you to the other side, and you want to keep getting correct answers until eventually you win the game of tug of war and you go far enough to the right, for example. Okay. A specific version of this heuristic that we'll be looking at in this talk is you get 1 point for each correct answer and you lose 1 point for each wrong answer. So there's this sort of a symmetry there in terms of the, one correct answer pulls you to the right. An incorrect answer pulls you to the left. And sorry, I should have said here, I'm assuming you can never go below 0. So you can never have negative points. And then you keep giving problems until a student gets N points. So we can look at different values of N, but we'll keep the structure of 1 point for each correct answer and minus 1 point for each wrong answer. And so here's the simple demonstration of this heuristic. You'll see on the upper right is the number of points a student has at any given point in time. Keeps going up or down, depending on whether they get things correct or not. And eventually they'll get 5 correct in a row. For example, so if N was 5, we would then assume that they've reached mastery and move them on to the next topic. Okay. So the tug of war heuristic is also used in practice. A variant of it is used in ALEX, the adaptive learning platform ALEX. And that was where I actually got the inspiration to study this heuristic. But it wasn't really, it's not really given a name in ALEX, so I gave it the name tug of war heuristic. But again, it's a variant of this heuristic. I'm not going to go into what that variant is. I'm happy to discuss that offline. But it's slightly tweaked. But for the purpose of this talk, I analyzed the tug of war heuristic which actually previously Alex did use another specific variant of the tug of war heuristic, not the +1 -1, but a different version of it. And so again, the main thesis of my talk, now we can sort of clarify it a little bit further, is that both of these heuristics, both the n consecutive correct in row and the tug of war heuristics, are optimal policies. I put optimal in quotes. I'll go over what I mean by that, for some variant of a Bayesian knowledge tracing model. Okay, so to make sense of what this means, we have to now discuss the Bayesian knowledge tracing, or BKT model. So again, this is a popular model used in knowledge tracing, and which the literature has built on over the past few decades. It was initially proposed by Corbett and Anderson in 1995, actually probably a little earlier, but the main paper that's cited for it is from 1995. So this model basically assumes that a student can be in one of two states. The student is either in this not learned state, where we assume that for the given, knowledge component or skill that we're trying to teach, the student has not learned it yet. Or they can be in this learned state where they have learned it. And once they're in the learned state, we assume they stay there forever. They can never move back to the not learned state. And every time we give the student a problem, they answer it correctly or incorrectly, we give them feedback afterwards if they get it incorrect, if they answer incorrectly. And based on that feedback, they can actually, they have some chance of learning the skill. So there's a probability, this P of T, the probability of transitioning from the not learned to the learned state. And then if they haven't learned it, there's some probability they'll answer the question correctly still. And that's the probability of guessing, right? There's some probability they'll guess. If it's a multiple choice question, for example, maybe there's a 25% chance they'll get it right, even if they have no idea what they're doing, right? In another case, maybe they can take a reasonable guess, even if they don't actually understand how to solve the problem, right? So maybe there's a 20% chance of guessing. Once they have learned it, generally they will get the question correctly, they'll answer correctly, but there's still some probability they'll slip. So they'll answer correctly with the probability 1 minus the probability they'll slip, which means they mess up, they do a typo, some simple error, and they get the answer incorrect. Okay, so these are the main parameters of the model. There's also the initial probability that the student is in the not learned state or the learned state, right? So this probability here is probability that the student starts in the learned state. So how is the BKT model actually used to implement mastery learning? It's used in what's often called cognitive mastery learning, which was introduced by Corbett and Anderson when they introduced the BKT model. And this algorithm basically says to keep giving a student problems on a given topic or skill until we are 95% confident that they've learned that topic or skill. And then we stop and we can move on to another topic. And in practice, sometimes we're teaching multiple topics at once. For the purpose of this talk, I'm just going to assume we're doing one thing at a time for simplicity. You might wonder where this, if you've not seen this before, where the number 95% comes from. It's somewhat arbitrary. We could choose, a larger number than like 99%. We could choose a smaller one like 90%. And the higher it is, the more confident we are. But there's a trade-off because we might give some students many more problems than they actually need to do. So if we want to reach 99.9% confidence, students would end up doing a lot of problems, and that's onerous on many students. And so that's not the best thing. So there's a trade-off, and 95%, might be a reasonable way to navigate this trade-off between making sure enough students reach mastery and students don't get too much extra practice. This was the number that was used by Corbett and Anderson, and it's sort of stuck in the literature ever since. And so we will refer to this cognitive mastery learning policy as the optimal policy for a BKT model up to 95% accuracy. Again, we can't say it's optimal because we can, in a sense, do better by increasing the number, but then it's worse for some students. So we'll say it's optimal up to 95% accuracy. And so later when I refer to an optimal policy for a BKT model, this is sort of what I'm referring to. It's the natural cognitive mastery learning policy for that model. Okay, so now we're ready to go back to the two heuristics I just talked about and reinterpret them as optimal policies for variants of BKT models. So first, let's look at the n consecutive correct in row heuristic. We can actually reinterpret this as the optimal policy for a BKT model where the probability of slipping is 0. So basically, as long as the probability of slipping is 0, and under some minor, constraints on the probability, the initial probability the student knows the skill, it doesn't have to be these exact values I give here, but it works for these ones. So I'm going to disregard this for now. Then it's the optimal policy for some n consecutive correct in a row heuristic. And for any value of n, we can choose the probability of guessing and probability of transitioning to make it optimal for that value of n. Right? So if n equals 3, you can look in my paper for more details. We can pick these values. We can pick a specific BKT model where as long as the probability of slipping is 0, such that it's the optimal policy. So why is this the case? Just to give some intuition, it's because as soon as the student gets a problem wrong, a topic wrong, we basically sort of reset that student. That is, the student has to get 3, let's say 3 correct in a row, right? So if the student answers 2 correct, then they gets 1 wrong, and 2 correct, and 1 wrong, 2 correct, this can go on indefinitely. We assume that they don't know the skill, because as soon as they get 1 wrong, they have to get 3 more correct in a row. It doesn't matter how many things they've gotten right in the past. So it's almost like once we know they've gotten something wrong, we know that they don't know the skill, and we sort of go back. We have 100% confidence that they're in this state, right? And that can only happen if the probability of slipping is 0. Because as long as there's some probability of slipping, then we should say, okay, the student's gotten a lot of things right, even if they got one thing wrong here and there. We're not 100% confident they don't know it. But if the probability of slipping is 0, as soon as they get something wrong, we are 100% confident they're here. Then they have to get 3 more correct in a row for us to be convinced that they're in this state. Hopefully that gives some intuition for why this is the case. Okay, now we can go on to the tug of war heuristic. And we'll see that in this case, it's a little bit more complicated. It's not really the optimal policy for BKT model, but it's the optimal policy for a model where we assume the probability of guessing is the same as the probability of slipping, right? So let's say, for example, the probability of guessing is 20% and the probability of slipping is 20%. So here, students who don't know the skill get it right 20% of the time, and students who do get it right 80% of the time. But we make no strong assumptions, or really no assumptions about how students transition from this state to the next, right? That is, it could be any probability. It could be 0.1 or 0.2 or 0.3, or the probability could change over time, right? The probability could decrease or increase as time goes on. Or maybe it's not even probabilistic. Maybe it just so happens that it sort of clicks for the student all of a sudden, right? And we make no assumptions about how that happens. Maybe, for example, this is silly, but maybe the student can't learn on Mondays and Tuesdays, but as soon as it's a Wednesday, they'll learn it immediately, right? Or sort of, it can be basically decided by an adversary, and it doesn't matter how this learning takes place. The tug of war heuristic is actually the optimal policy in this scenario. So we don't care how this learning took place, and we don't know how this learning takes place. We're not going to make any assumptions about it. If that's true, if we don't make any assumptions about how that learning takes place, then in a sense, the best thing we can do is actually the tug of war heuristic, which is pretty interesting. And what I mean by optimal, I put optimal policy in quotes here because it can't be exactly optimal. Because, for example, given that I'm making no assumptions here, it's possible that a student will just never learn, right? We have this phenomenon in the literature called wheel spinning, right? This model can account for the fact that for some students, there might be wheel spinning. So if a student never learns, at some point, this algorithm is going to probabilistically declare mastery, right? Oh, it looked like the student got it right a few times. It's going to think the students learned, even if they haven't eventually. But we can choose the value of n to make it so that our probability of sort of a false positive will be delayed as much as we want, right? So for example, if a student never learns, we can choose, for a value of n equals 5, for example, it might be that for over 100 time steps, we'll never declare the student knows the topic if they've never learned it, right? Or at least for 95% of students, and this is where that 95% comes in here, for 95% of students, it will take over 100 time steps before we declare mastery for a student who never learns it. That's the kind of guarantee we can make in this case. It's a little bit different because we're not making a probabilistic assumption here, which we were before. Okay, so hopefully that makes some sense. Again, you can refer to the paper. I have supplementary material online, which goes into this a bit more detail. But actually, I'll give you another resource that you can look at, because this is actually a special case of the Bernoulli-Kusum algorithm. So this problem that we're studying here in the general case, if we have a BKT model, any BKT model, notice that now the probability of guessing doesn't need to be the same as the probability of slipping, where we don't make any strong assumptions about how the learning takes place. This is an instance of the change point detection problem in statistics. And this is a problem that's been studied in statistics for decades, dating back to the 1950s. And the algorithm, the optimal algorithm, the optimal solution for this problem is actually the Bernoulli-Kusum algorithm. So you can look up this algorithm, and it turns out that in the specific case where the probability of guessing is the same as the probability of slipping, it's identical to the tug-of-war heuristic. But seemingly no one in the AI and education community has sort of framed the problem of mastery learning in this way, where we don't make assumptions about how learning takes place, right? And so I've never seen the change point detection problem being applied in this context. But interestingly enough, even though this connection hasn't been explored, learning was actually an early motivation for change point detection. In one of the earliest papers on change point detection by Page, he actually considered learning, trying to detect when learning takes place as an application. And you can read this quote for an example of this that he gave. So to conclude, what we've seen is that both the n-consecutive correct and row heuristic and the tug-of-war heuristic can be justified in terms of model-based assumptions, right? In particular, variance of the BKT algorithm. I want to state that the n-consecutive correct and row heuristic may not be that reasonable if we assume that slipping is possible, right? If we think slipping is not possible in a given case, that if a student learns something, they're going to always answer it correctly, it's very simple, very straightforward, then it's a reasonable heuristic, I think. But if we assume that, there's a 10% chance or 20% chance that students might still get it wrong, even if they know it, they might make a typo, especially if it's a complicated problem, right? Or students are just, maybe they're not paying attention, right? When they're doing these problems, then it might not be such a reasonable heuristic, and it might punish students for getting things wrong when it shouldn't, right? So basically, by reinterpreting as a model-based algorithm, it can sort of tell us when it might be reasonable and when it might not be reasonable. And it hinges on, how likely it is that we think slipping might actually take place. On the other hand, the tug-of-war heuristic seems to actually be particularly robust to different assumptions. That is, we didn't make any strong assumptions about how that learning takes place, other than the fact that we assume that the student either knows the skill or doesn't know it, right? And we can actually show, I didn't have time to go into here, but I'm happy to talk about it offline, that in simulations, we can actually show that it does reasonably. In fact, it does about as well as the optimal BKT algorithm, assuming a particular BKT model is true. And the nice thing about the tug-of-war heuristic is that if we misspecify the BKT model, for example, let's say we fit a BKT model to data from a particular school or set of schools, and then we want to deploy it in a set of schools where students actually, maybe they're slower at learning or they're faster at learning. It might not do very well in practice, but the tug-of-war heuristic, because it doesn't make strong assumptions about how students are learning, what that probability is, it can be, the same algorithm can be deployed in different contexts. I think it's also important to consider other practical aspects, right? To determine what should actually be used in practice, we should consider what enhances the overall student experience, right? It might be that one algorithm or heuristic is actually suboptimal in some sense for students, but it might still be worth using in practice. And maybe that's why, these adaptive learning platforms are actually using such heuristics. For example, heuristics can be easy to understand and easy to explain. The n-consecutive correct and row heuristic is very easy to explain to a student. Similarly, the tug-of-war heuristic, it's quite easy to explain to a student because it's, in a sense, it's similar to games. You get a point, you lose a point, and you want to get, enough points to move on, right? On that note, heuristics can be motivating and they can be gamified. And so they might be more engaging than using some black box algorithm or some algorithm that's difficult to explain to the teacher or the student. On the other hand, I think sometimes heuristics can be demotivating. The n-consecutive correct and row heuristic, for example, because again, it can punish students for getting one thing wrong, even if they know it, right? Even because maybe they slipped, that can actually be demotivating experience, which I've heard from students, in my educational technology class. And I'd like to conclude on this thought that as researchers, we shouldn't just be focusing on how to apply state-of-the-art approaches, from AI and machine learning to education, but we should also understand the techniques that are actually being used in practice, both in educational technologies or in the world of education, K through 12, and higher education more broadly. And sometimes this could lead to discovering new ways of doing things, right? Or possibly even old ways of doing things, which I showed in this talk. That is, as I went through this process of trying to understand if these heuristics are reasonable, this actually brought me to the change point detection literature, which I wasn't aware of before, and I realized that it's actually might be quite a reasonable way to do mastery learning. And so, this exercise of actually trying to understand what happens in practice can be rewarding because we can try to sort of bridge the gap between research and practice, but it might also be rewarding in that it could lead to new research directions in the future. Thank you for listening.